there are 3 questions. They're nominally about 100 each. Some are a little more, some are a little less. So the total is out of 300. Full score is, 330. Full score. The total score you can get is 330, and a full score is 300. So there's a 10% surcharge in your favor on those. 3 questions. First one is on material properties, viscosity, compressibility, interfacial tension, density, the stuff we dealt with in the first week. The second question is on fluid pressures on structures, maybe with ideal gas law in there. Third one is on accelerations, accelerating fluids. So that's the spectrum of topics, I guess, that are on them. Nominally, it's a 90-minute exam. I don't think I'll be there, but I think you'll probably get as long as you want to do it. There'll be an interesting test tonight. The 8:15 class, I think there's nothing that comes afterwards. So since both these exams are at 8:15, you can probably stay for 90 minutes plus. After 2 hours, probably people will start getting restless, and it might be the point of diminishing returns. But my hope for you is that you can show your stuff, and you've certainly soaked up a bunch of stuff that you've been exposed to in the last little while, and there's no desire to rush you. You should think about what you're doing. You should go through it methodically and show your skills in the best possible light, and put yourself in an unassailable place the rest of the class. I think that's what I'd like to see you come out of it. The scores, if we're less than 300, we'll take the highest score up to 300, and everyone will move up by that. But there is, as I mentioned at the beginning of class, there is no curve. I don't know that necessarily works against you. I think it works actually for you. I think in the scores from last, the basic desire, I'm not trying to get an audience so I can proselytize to you, but the basic idea is I want you to know something about fluid mechanics so you don't either hurt yourself or someone else, and they're a credit to our programs. And so that's what we want you to be able to have the minimum and more than the minimum capability in that regard. So it's kind of a static requirement, not based on a moving target with a curve. And so the thing that works in your favor is that there are typically much more A's from a way of scoring that than there are otherwise. And then the tail end of the people may be the people who are not here tonight. I'm not sure. I counted about a couple of 150 or 160, 70 people. We have 300 in the class. So as I mentioned early on, there are no marks for attendance, but hopefully there is some value added from coming to class. I don't know, or at least looking at the stuff online. So what I was going to do today was just go through some of the background that we've gone through in the last 4 weeks and give my perspective on it. And there's a document which is on Angel, which I mentioned in this email, which is the one that we'll use today. If you want to ask questions about this document, you should interrupt and ask. If you want to stay beyond this and ask questions about past exams or whatever, then I'm happy to do that as well. So I'm basically yours to do what you wish with, to some degree, I guess. Yeah, I probably shouldn't go too far with that, I suppose. I realize I'm vulnerable up here. So that's the plan. And so I bet you I can outlast you, though, in terms of my engagement to fluid mechanics. Does that sound okay? So that's the plan, right? So any questions about the logistics? Double-sided piece of paper, 8 by 10, no, 8.5 by 11. You can put whatever you like on it. Calculators you'll need. Pens, pencils you'll need. Nothing else. Everything else is on the sheet. You'll have noticed in past some exams are multiple choice. We don't do multiple choice anymore for reasons I've mentioned in the past. And so they'll just be questions. They're like the homework examples, except they kind of lead on to each other. They're graded by TAs, not for single final answer, but partial credit for whatever you've done. And so if you don't know how to do something, you should try and write something down anyhow and try and work your way through it. If you've made a mistake in one question, we don't necessarily follow that over into the next question. We cut you the benefit of the doubt in that. And if you have questions about the questions, then you should ask them. There are two people roaming in each of the classrooms that you can ask. It isn't supposed to be a test of, I know we have a decent number of students for whom English isn't their first language, and it's not supposed to be an English language test. So if you don't understand something in terms of a term, ask, and hopefully all will be revealed. Okay? So, ask. So. Yes, sir?
Are we given that equation sheet, or do we have to...
This is on a, no, you're not given any equation sheet. What you need to bring is what you want to bring.
So should we have conversion factors on our cheat sheet?
There will be no units other than SI. And I would expect that you know, no, it's on the exam. So no, you should know what a Pascal and a meganewton, a Newton per meter squared are. Work energy you don't need to know yet. You should know what density is. No, I don't think you need conversions. But you should know what newtons per meter and how to. You should know how to dimensionalize things like you did in your first chapter, right? In terms of mass, length, and time units. Yes. The test will all be in SI. Some tests I noticed today have been in English units or BGS. This test will all be in SI. SI only. That's all we've used in class so far. Period. Like what? You should probably know that atmospheric pressure is 100 kPa. You probably need to know, I think it is given, yeah, they are given, but you should also know that density of water is 1,000 kilograms. The density of air is about a kilogram per cubic meter. So, yeah, I think you're given most of them. So I don't want to enter in a contract with you. I guess that's really what I don't want to get into. But if you think there's something that you need, you should bring it. I don't think you need to, you certainly don't need to make conversions outside SI units. But you should know the basic units that we've messed around with in class. You should know that absolute zero is minus 273, etc. Kelvin. Or 0 Kelvin is 0 is plus 273. 0 centigrade is 273 Kelvin, etc. Yes? Yeah, I've never scrubbed calculators. You probably should be. You probably shouldn't bring equations in on them. I'm not going to scrub them. I guess my philosophy is that the questions have enough of a subtle twist to them. It's just not plug and chug. So it's not what equation do I need to solve this. You have to actually think about it. So bring calculators. Programmable calculators are fine. Okay. So I'm never quite sure how to do this, but I'll go through this, and I'm not. Well, that's you have all of these. So, in terms of any other questions before we get rolling? So this is actually marked up from last year. I didn't realize that. So I use this program called Skim, which allows me to mark up as we go through. If you store it as a PDF and look at it in a regular PDF viewer, it doesn't actually store the markup, or it doesn't show the markup. But when you show it in Skim again, it shows it. So these are my markups from a year ago. So it's not particularly a specific review sheet to this exam, but it does cover everything, all the concepts that you need. They're relatively straightforward. So ideal gas law, you know in terms of gas pressure, temperature, gas constant, this being the specific gas constant for a particular gas, this being the universal gas content and the molar mass, and this being the density. Density, of course, is mass per unit volume, I guess uppercase M per unit volume, just by definition, which leads to some of our expressions. Remember always, I can't believe if you're taking thermo now, you don't remember that this is absolute fluid pressure, this is absolute temperature. Otherwise, you'll get the results wrong, so you have to remember about doing that. And if you look at any particular gas, you can merely write this expression as pressure is equal to density gas constant times temperature. And if you look at the ratio of pressure to density for each of these, this is exactly where this expression comes from. So if the temperature doesn't change and you compress it, then the ratio of pressure to density is always the same. Irrespective, you increase the pressure, you also increase the density in the same ratio, so you know that. If you compress them isentropically, so not where you put it in the gas, in the pump, and you close it and you keep the temperature the same, but you put it in a pump and you insulate it so you keep all the heat in there as you compress it, then that still applies, except there's some correction factor on here, which is a constant, which is typically for air it's about 1.4. It doesn't really matter. You wouldn't need to know that, for instance. You'd be given something like that. If you needed to know molecular weights of something, you'd be given those. If you needed to know gas constants, you'd be given those, etc. So you've certainly seen the ideal gas law and know how to deal with that. Compressibility, well, we used it in a variety of different things. It's really just a term. It's useful to us because we used it in defining acoustic wave speeds, but we haven't really used it for anything other than that. Just by definition, it's the change in volume over a unit volume with a change of pressure. The negative sign is just the fact that it's if you increase the pressure, the volume goes down. So just to keep this constant, a positive unit or a positive dimension, it's a negative in there. It's exactly the same as the change in pressure eliciting a change in density. They're exactly the same expressions. And the compressibility is just the reciprocal of the modulus. So it's the same as electrical conductivity is 1 over the reciprocal of resistivity, electrical resistivity. So compressibility, and this is bulk modulus, I guess, right? As we defined it. So if you want terms attached to this. A kind of interesting quirk, don't think you need it in the test, but don't turn off, is that the modulus of a gas at relatively low pressures, actually up to quite high pressures, is equal to the gas pressure. So at 100 kPa that we're sitting at right now, the modulus of air is 100 kPa. So interesting quirk. So gas law is an important law. You will need gas law, I mentioned that. Viscosity is a way to be able to relate forces that you apply to bodies that are moving to the velocity at which they're going at. I think you've done some examples. It's really just Newton's law of viscosity. It's it's a straightforward law. All it says is that the stress that you apply, the shear stress that you apply in a fluid, is equal to some constant, which is the dynamic viscosity, which is in SI units, it's units of Pascal seconds. Shear stress is in pascals. And the shear stress is proportional to it's a kind of a shearing rate or a velocity with space. So the easiest way to think of this is a derivative, but it's also just the change in velocity as you go from one location to another. So if you drag a plate with a fluid underneath it across a static plate, then if this plate is being pulled by a force and it's moving at some velocity, which would be the velocity that's actually on this plate here, then the rate of change of velocity with space in the normal direction, so it's the rate of change, it's the change in velocity in the x direction, so let me write it out, tau equals mu, the change in velocity in the x direction with respect to y. Right? This is the y direction here. So as you go in this direction, this is delta y if you want to think of it, and if you want to think of it, this is delta v, and these are the two components that make that. And so I think you've done some examples with that in your assignments to be able to say, for instance, if you know what the shear stress is that's applied here, then, for instance, you could calculate this force. This force would just be equal to the shear stress that's applied on this plate multiplied by the area of the plate, right? So stress times area gives a force, just by units. And so that's another expression. So ideal gas law, Newton's law of viscosity. We will only deal with, we will only deal in this class with Newtonian fluids, which are these ones here, which basically say that if you increase the shear, if you double the shearing rate, so if you start off with a shearing rate of some magnitude, you'll have to apply a specific shear stress to move it, a certain force. If you double that shear stress, shearing rate, then you have to apply double the force to be able to. That's basically the definition of a Newtonian fluid. So this is 2 dy dv, right? dvx. 2 dvx dy. So it's just double the amount. So that's the definition actually of a Newtonian fluid. So ideal gas law, Newton's law of viscosity and how to use it, interfacial tension. That's interesting. So yeah, I didn't know I was so generous. I think that question was actually on the test last year, and so you might check that. I'm not sure. So interfacial tension. Interfacial tension is the third of our major properties that we've dealt with. We looked at, for instance, the behavior of a capillary and derived an expression related to that. And you might have looked at some other ones in your assignments. I can't remember. I will say one other thing is that I don't really know what your assignments are. So, and I haven't looked through the book to pull out questions from those assignments. So that's just another data point for you, I guess, as much as anything else. But if you want to be able to look at the roles of interfacial tension, then interfacial tension is applied where there's a free surface, a surface between a liquid and a gas in this particular case, and also a solid. And so I think either last year or the year before, the question was, perhaps it was 2 years ago, because I can't imagine I was that generous. What's the maximum diameter of a needle that can float on water, if it's made of steel or if it's made of copper or some other component? And so you just write the free body diagram for it, which gives you the forces that are acting upwards, in this particular case T and T on each side. They're applied along the length of it, so this is equal to newtons per meter. This length is meters, and so in terms of units, this is newtons. There's two of them because they're both acting upwards, and the only component you have acting down is the weight of the solid. And I think the question said ignore buoyancy, so you don't have to worry about the fact that half of this is submerged. So, but we did an example for a capillary tube. It was basically the same idea. What did we do? We said that what we wanted to do is we wanted to be able to cut this off at this point here. And the reason we could do that, because we haven't defined it yet, but we know that if you can go from one point to another in the fluid, and that point is on exactly the same elevation as you go along this pathway, then the pressure here has to be equal to the pressure here, by definition. So what you can do is you can just cut this tube off at the bottom, and if you cut the tube off at the bottom, you can just do a nice free body diagram to be able to calculate behavior. And I won't go through it again, but basically the idea is the weight of this, which is, well, the volume times unit weight of the fluid, and the forces pulling up here, which are going to be equal to interfacial tension times circumference. You can check that each of these are forces, you balance them for each other, and then you define behavior in terms of this particular radius or diameter. So, straightforward. Well, straightforward to me. Typically, you could think of this axis as an angle, but you can also think of it just, the simplest case is just if it's parallel to the glass that you have, in which case it's much easier. This expression here is exactly the expression that comes out of that. And if theta is equal to 0, then this term just is equal to 1. It drops out. So we have a relationship between a height rise as a function of interfacial tension. And we talked about it in class. Interfacial tension is higher, it rises higher, radius of the tube gets smaller, it rises higher. All the things that you kind of know intuitively, but put numbers on it. Okay. So, a question on fluid properties. So those are the principal fluid properties, I think. So, ideal gas law, viscosity, and interfacial tension. So know how to use those. I won't go through these because we'll go through this when we talk about things. We spent some time talking about fluid pressures at a point. And do you have that? Did I not put that in? You should have it. And so we derived some expressions. If we look at just the static case first, then this expression here is true wherever you write it. It's true for gas, it's true for liquid. I say it's true for gas because gases, as you apply larger pressures, as you get closer to the surface of the Earth, the density is larger. And so the magnitude of this increases as you get closer to the Earth. As you go into the atmosphere, it's smaller. But this expression is true everywhere. Absolutely always is true. So it says that the rate of change of pressure with elevation as you go up or down in a liquid is equal to the negative of the unit weight. The reason, again, for this negative sign is to remember that we always use our... Yeah, I apologize for having these scribbles on here. I didn't choose that, but this is the first time I opened it up. So remember the fact that we always choose our positive z direction upwards. And so the fact that pressure is changing as you go deeper, increasing as you go deeper, only is true because dz is decreasing in this case, pressure is going up, and to be able to make that work out, you need a negative sign in this. In a liquid, it's relatively straightforward because we can rewrite this just by integrating it as the pressure being equal to the pressure, a new point being equal to the pressure at another point plus the unit weight times the elevation difference. The vertical elevation difference, not the angled elevation difference. It's the elevation difference. If you add an extra fluid pressure on the surface, then physically this curve, which is really represented by this behavior here, right? If you add an extra fluid pressure on the surface by surcharging it with a gas or another liquid for that matter, then all you do is you physically shift this over by some amount by adding another amount, which is exactly what this is. And so you know plenty to think about how fluid pressures change with elevation. So two important expressions, I think, are this, to some degree, and perhaps more importantly, the integrated form of this expression, which is either this, depending on which you prefer to use, or this, right? That's behavior for a liquid. Okay, so I think you certainly, if you've got this far in your homework assignments, you certainly know how to do that. Okay, everyone okay? It gets a bit more complicated when you deal with gases. There isn't a question for which you need this this page of formula, I don't think. So don't switch off, though. So we made the point that this expression is valid everywhere, always, liquids or gases. But for gases, because this isn't constant, it changes. Unit weight, of course, is equal to density times gravity. And density is a function of pressure. Not trying to confuse you, this just means it's a function, I guess, a function of pressure, right? And so because this changes with pressure, then if you go up in the atmosphere, you have to do some manipulation to it, and we did that manipulation, and we came up with an expression which was this, which I think you needed to use last time. If you check your last year's...
I have a question.
Yeah, okay, I'm listening.
Is there any chance at some point we can go through or look over exam problems or stuff like that?
We can do, yeah. I'll do it after this. I'll go through exam problems if you want. If you pick them out and ask them to. I mean, I'm not going to go through the exam problems we have, but if you have some ones that you want to go through, I'll do that.
Okay.
Yeah. And so you just need to wait till we got through this part. So you don't need to know the stuff for pressure changes in a gas. So if we summarize behavior for liquids, we know that pressures act in the same direction at a point. and same magnitudes in all directions at a point. You know, if you go horizontally, this is how we were able to, for instance, be able to calculate the changes in pressures as we go across in the capillary tube. This is exactly the expression that we used. Is that if you go horizontally, there's no change in pressure, and so the pressure inside the bottom of the capillary tube is exactly the same as the atmospheric pressure outside. And we've already talked about this, so you have that. So you know that every point within a horizontal line within a fluid is the same pressure. So in here it has to be atmospheric. Here it has to be atmospheric plus the unit weight times the height. You can do exactly the same in here, and that's what manometer equations are all about, is being able to work your way from something that you know, which is atmospheric here, to a pressure which is larger than that, going from this to transfer to this elevation, and then being able to, for instance, be able to calculate what this is just by subtracting off those. So that's really all manometry is all about. You'll remember the manometer rules. They're written here. So if you go up in a fluid, you subtract. If you go down in a fluid, you add. And you just work from one location all the way to a location that you know. So for instance, if you want to know the value here, A, you just, in this case, you could just scoot straight across here. You know that pressure here is the same as pressure A. You subtract 2 meters times the density of this water here to get to this point. You add 7 meters to get to this point, and then that should equal the atmospheric pressure. And so you just have to keep account of the fluids that you're in. So you know, for instance, you know that if you're in a liquid, you probably have to take account of the unit weight. If you're in a gas, you probably don't if there are other liquids involved, because the density of gases may be an order of 1,000 times less.
In the book, we had problems that had manometers on an angle.
Yeah.
But we haven't done one of those in homework. Should we be concerned with going over those, or are we looking at purely, vertical, doing that type of thing?
We did one in class.
Yeah. And there was one on the homework, but it said disregard the angle.
Yeah. Yeah, I think anything we've done in class is fair game. So yeah. And so, yeah, there's not necessarily a differential manometer question, though. But, yeah. Okay, so go up, you subtract. Go down, you add pressures. If you go up in a gas, then maybe you can neglect the magnitudes of the unit weight. Okay. I'll be happy to go through some questions, exam questions, or whatever other questions you want to do after the fact. So one of the reasons that we want to get fluid pressures at a point is because we also want to be able to say something about fluid pressures on structures. And so if you remember when we talked about that, I guess there were 3 key components. The first is that if you want to get the fluid pressure, the force that acts on a structure, we need to find the resultant. If you want to find the resultant, you can always get the resultant by calculating the magnitude of the depth of the centroid of the plane, the unit weight of the fluid, and the area of the plane as well. And so this is always the vertical, this is always the force that's on a plane surface only. This is always the depth to the centroid of the plane that it's acting on, not the point of action, not the center of pressure. It's always a vertical distance. This is unit weight, which is just density times gravity, and this is just the area of the pressure. So the first thing that we need to be able to get is the magnitude of the resultant. If we want to know where it acts, we need to know the center of pressure. And we can do that by a variety of ways. We can use our second moment of inertia expressions to be able to do it. That's bomb-proof. It works all the time. And we can look at that in a second. Or you can do it just by resolving forces around some arbitrary location to resolve for the lever arms. You can do it either way. But both of those apply to the behavior for forces on a plane. And then if you want to see how something fails, we'll come back to number 2 in a second. If you want to see how something fails, then you have to resolve around a failure mode. So once you have all the forces that are acting, you know where they act. To know whether it falls over or not, you have to choose a way it'll fail. So there's a pivot or a hinge or a way of moving. You need to be able to define that. And so we've talked about that in a number of examples, and we can go through one if you so wish. The magnitudes of the forces, again, if you have a plate and you know where the centroid of that plate is, and you know the depth of that centroid to that centroid from the surface vertically, you have HC. So the plate doesn't have to intersect the surface. It can intersect the surface, in which case it should just be the wetted portion of the plate, I guess. But it doesn't have to intersect the surface. The area speaks for itself, and the unit weight of the fluid. It doesn't matter if it's flat. For instance, if you have fluid up here and you have a plate down here, the depth to the centroid of that plate is the same distance if the plate is flat or if it's inclined. And actually the forces that are acting on that plate would be exactly the same through all the angles of inclination for that, because this, as you can see from this expression, and all it's saying is that if you look at the distribution of pressures at this point, they decrease above it and they increase below it, but on aggregate they're equal to the average amount, which is here, I guess, which you could draw. You know, you have an inclined plate and it's below the surface of the water, then the fluid pressures acting on this would be some distribution here, which would be equal to Z1. So this would be P1 Z1. Sorry, that's not right, is it? So this, the pressure acting here would be equal to Z1 multiplied by the unit weight of the fluid, which would be this amount. And the part that's due to the other component, as you get deeper, is this. So physically all it's saying is if you go to this midpoint here, which is, I'm running out of space, this is H sub C, right? All it's really saying is it's taking this magnitude as you go up here, it's cutting off this bit of the triangle, and it's putting it on here. And it's calculating the distribution equal to this area, which is this length, this fluid pressure, which is equal to unit weight times HC. So this fluid pressure here would be HC times the unit weight of the fluid, and therefore the total force that's acting is just going to be the product of those two. The pressure that's acting, which is this, multiplied by the area. So it's no different from this. So I'm not trying to confuse you, I'm just trying to give you some maybe insight into what's going on, because I think that's what you need to gather. So you can always get the fluid pressure from this simple expression, always, on a plane surface. If you want to know the location where it acts, you need to know something about the center of pressure. If you want to get the center of pressure, you can use these stock expressions. The important thing to remember is that for this expression here, this is the vertical depth to the centroid of the plate from the surface. Vertical depth. Has to be always. This is the in-plane length from the surface to the centroid of the plane. And so physically what this expression means is that the point at which the force acts is going to be equal to, it's going to act at the centroid, the centroid of the plane plus some small amount. And that small amount is because of this pressure distribution weighting the larger pressure below that point relative to the higher pressure due to the sloping pressure distribution above it. And so as you can imagine, if you look at just physically what it means is if you look at a vertical pressure distribution, and if you look at, for instance, a plate that sits here, then the location where the resultant acts is going to be 2/3 of this direction down, right? Just from what we know. And a third up from the bottom. But from what we've just said before, is if you take the same height of a plate and look at it here, then again, the pressure is going to be a third of the way up from this, but it's going to be weighted by this amount which acts through the middle of this distribution. So basically the point of action at this point is going to be much closer to the centroid of this plate than it was from this. The maximum it can be is going to be, I guess, a sixth away from the centroid, in this case, right? This is a sixth, the difference between the center here and the bottom here. And this one is going to approach the magnitude of the plate. So, but you can use that just as a stock expression. All right? Yes?
Is the moment of inertia going to be given to us?
Yes, has been in the past. And so you might know the ones for some simple cases, but yeah, if you need it, you'll be given it. Yeah.
Question, can you just go back up a second?
Yeah.
Like, for the 2/3, 1/3 thing,
Oh yeah, on this?
yeah, what is the shape of that plane? Is that just a rectangle? I thought that was dependent on the shape of the plane, not the shape of the
It is. It's just a rectangle. It has to be a rectangle for that. So it has to be one into this. Yeah.
So if that was like a circle, then we would use the, or like a half circle, then we would use the I, C, and all that stuff down.
You'd have to use the second moment of area around the x-axis. Yes.
Okay, so the 1/3, 2/3 is
Always applied. So this expression only applies for a plate. So yeah. So that's actually a useful point. So this expression only applies for a plate. A plate, flat plate, can be angled at any angle. Could be any shape, but it has to be planar. And so YR applies to that. If it is a plate that looks like this, then you know that where it acts is a 2/3 of the way down and a third of the way up, just because of the pressure distribution. If it's a circle, and you can of course get that just by using this expression here, just by using this. If it's a circle, for instance, then you'd have to actually use the second moment of area. Okay. So everything we've talked about is only for plates, so for flat surfaces. Moments of inertia we've talked about in class. I don't want to complicate matters by saying that, of course, the point of action is actually the balance point of the pressure distribution, which we've said a number of times in class, but that might just confuse matters. Everyone okay still? Fluid pressures against structures. Yeah, you can get it just by using this for a plate that intersects the surface. It's going to be equal to 2/3 down, third up from the bottom. We always know that. You can always do a simple moment, sum of moments, to be able to do it for any body that, for instance, doesn't go from the surface. So, for instance, if you wanted to solve out the location where this acts, what you could do is you could choose this as your origin here as y equals 0, and you could calculate from that formula the magnitude of y sub r. And if you use that appropriate expression for this plate, you'd get the right value of y sub r. So if you use this expression as you have done, then you'd get the right location where this force acts, the force being given by this magnitude, but it acts at this particular location. And so you can certainly get that by using that expression. The other way you can do it is just by taking moments around some arbitrary location. And that is that you have this uniform distribution. You know that the force acts halfway along it. And so if you take the total magnitude of this force and multiply it by L over 2, and you add to that the total amount of this green force, and multiply by a lever arm of 2L over 3, which is the lever arm for this, and you provide a force acting backwards, which has some location that you don't know, then you can solve for this because you know that the resultant is just equal to the sum of these two distributions, right? F triangle plus F square. Okay? So you can take those. So remember the three things, right? force acting, the resultant is always the depth of the centroid of the plate multiplied by unit weight of the fluid and the area. The location where it acts is always YR. So the depth of the centroid, HC, is this vertical distance. The distance to the centroid is the in-plane distance from the surface of the water. And once you know where all the forces act, if you want to know whether this hinge can go, then you actually have to resolve around the particular location that's going to define whether it fails or not. So those are the three cardinal rules, if you like, for dealing with this. Okay, so this is just an alternative. This is the same way as using Y sub R. We did some examples in class. We can do them again. As I say, everything's in SI units, but just to resolve these, I'm happy to go through them again. You can find them on YouTube as well if you want. The question is, what are the forces that are acting in these particular geometries? Well, you can just draw a free body diagram. I'm sorry it's all scribbled up. I didn't realize that. But you know, for instance, that the vertical force acting down here is going to be the weight of the fluid. Has to be equal to the reaction, which is due to this. So you only have those two forces acting. So you can definitely write that these two are the case. And if you know the area of this quarter section and the unit weight of the fluid, you can certainly get the weight. Right? Weight is just equal to volume times unit weight. And the horizontal forces have to equal as well. So this you can isolate as a free body. If you had to apply a force to be able to keep this water in here, then the pressure distribution you'd have to apply would be this distribution here. And so this would be, from what we've just said, this would be 2 over 3 times 3 feet, which is 2 feet. So it acts a foot up from the bottom, and you know where it acts. And of course you can calculate the force that's acting. What would the force be that's acting? The force is equal to the unit weight of the fluid times the area times the depth of this. So the depth of the centroid is what? It's 3 over 2, right? Half this height. The area is going to be 3 times whatever the length into the page is, 1 foot length. So this is going to be equal to 3 times 1. And the unit weight is the unit weight of fluid. If you want to, you can resolve forces since you know the magnitudes of both the vertical and the horizontal forces. So if you just use Pythagoras, you can get the magnitude of the resultant for each of those, if you so wish. And in this particular case, because all of the forces are acting perpendicular to this, the fluid pressure is acting here all perpendicular to this, they all physically act through this point. So you know that the resultant would act through this point as well, if you needed it. And so you can calculate that. All right. If fluid pressures, if a container is filled with something that's not a liquid but a gas, for instance, then you might be able to neglect the unit weight. For instance, in this particular case, if this was capped off with a lid, and instead of having liquid in here, then what would be the pressure distribution that you'd have acting on this? Well, certainly in a liquid, then the pressure distribution would be varying linearly. In a gas, the pressure distribution, whatever it would be much closer to this. It has a very small gradient, right? So this is water, then this would be a factor of 1,000. If this was air, then this would be a factor of 1, just the difference in densities of the two. And so in some cases when you're dealing with gases rather than liquids in the system, you can actually consider that the pressure doesn't change markedly with depth, in which case it simplifies your calculations a fair bit. So I won't go through this one. So, all right. I went through this in class as well. I don't know if you want me to go through that. I think you can look up the video. I think the key point in many of these situations are that you can draw any kind of free body you want, and you can divide that free body to be able to look at the system in any way you wish. And so you can draw this basically as a free body on which you have fluid pressures acting. And if you know what those distributions of fluid pressures are, in this case, the only component of these are in the vertical directions, right? These small little wings in here is self-weight. So if you're resolving horizontally, as this question is, you don't care about those. I suppose you might think, for instance, that the magnitude of the fluid pressure that you have acting on this side would look like this. But of course it can't, right? Because we know that if you can go from any single point, such as here, so if you can go from this point, you know that the fluid pressure at that point is equal to 3 feet times the unit weight of water. And so since you can go from this point in a connected path all the way to this point, then the fluid pressure here can't be atmospheric. It actually has to be exactly the same pressure as this point. And so the fluid pressure distribution there would be this magnitude, because this fluid pressure has to be that. Okay? And so I think that's the trick from that example. All right, so fluid pressures on structures. Get the fluid pressure to point to get the magnitude of the resultant, get the force, which is equal to the depth of the centroid, unit weight times area. Get the location. You could either resolve around points, or you can use the second moment of inertia expression to be able to do that. And once you have those forces and know where they act, resolve around the force. I'll be happy to go through an example of your choice afterwards, if you so wish. Buoyancy. The buoyant force that's applied on any structure is just the displaced volume of fluid multiplied by the unit weight of the fluid that's displaced. It's entirely general. It doesn't matter what the shape of it is. So this expression is merely the expression that we have here. If you look at previous exams when we've had balloon questions, for instance, we've talked about those because we've had those in class, and so we haven't really talked about that so much. So you can gauge what might be fair game on this exam. I'm not trying to trick anybody, by the way, in case you're concerned. So prior exams might have been favored because we talked about some certain things in class which we haven't necessarily done now. But buoyant force is always equal to the unit weight times the volume that's displaced. You can always resolve things in terms of, again, a free body. In this particular case, it would be a tension acting downwards. It would be a buoyant force acting upwards. And it would be any weight of this component which is acting downwards as well. And you can resolve those to be able to calculate tensions in cables and things as you've been asked to do in the past. And so that's the other wrinkle, I guess, on fluid pressures on structures. And of course, buoyancy really is just an excess fluid pressure on a structure, as is kind of illustrated here. So in other words, if you take this, instead of thinking of it as a buoy, which is circular, and if you look at how fluid pressure changes with depth, the reason for buoyancy is just the fact that as you go down at depth, you have a certain force acting on here, which is equal to the pressure that's acting on this top surface. You have a larger pressure acting here because you're at a deeper depth. And the reason that happens is because you've got the weight of the fluid in here that balances that. If you take that weight of fluid out, then all of a sudden you don't have that vertical reaction, and therefore it wants to float up like a balloon or a football coming out of the water. So the rationale for it is simply that. And of course, the other thing that we've mentioned is that if you look at, for instance, changing the fluid pressure, because you're changing the fluid pressure on the top of this by some extra small amount here, and you're changing the fluid pressure on the bottom by some extra small amount here, changing the fluid pressure doesn't change the buoyancy in any way, because you're merely just incrementing the fluid pressure above it and below it by the same amount, so they both cancel out. So buoyancy doesn't care about anything about the fluid pressures that are applied in the tank or anything else related to that. It's just the unit weight multiplied by the volume of that fluid that's displaced. Okay. Talked about linear motions. Again, apologies for scribbles. What are the key points in looking at this? The expression that we used for vertical changes in pressure is this one, where the accelerations in all the other directions are equal to 0. And those are the expressions that we used. If the accelerations are not equal to 0, then you have to include those components. I guess there were two kind of standard results that we had. The first standard result is what happens if you accelerate something with a free surface. What happens to the inclination of that free surface? And just from taking a glass, you can imagine as you accelerate it, not with constant velocity, but as you accelerate it, it should incline. And we can basically develop an expression. You won't have to develop this expression, but the expression to get the change in elevation of the surface of a fluid as you accelerate it would be something like this. So this is a fluid that you have in a beaker. Acceleration in the y direction is the horizontal direction. Acceleration in the z direction is vertically upwards, again because we have our coordinate system which is positive upwards. And so as a result of that, you can get the inclination of the free surface that would act as a function of that. Gravity always acts. If you don't accelerate it upwards but just accelerate it horizontally, then this term would be 0 and this would be something. And so you can use that, for instance, to be able to calculate the inclination of a meniscus. We did it for a bus going down the road in class, right? To be able to figure out what the acceleration of a bus was, just from looking at this expression. The other way to think about this, so we can come up with something that says something about the inclination of a free surface, and there certainly have been questions on that in the past. The other question is, what happens if you're sitting in this fluid, which maybe has a free surface, and you go down in it from the surface? And the question is, how does fluid pressure change as a function of depth? And so this is minus z, I guess, in this case. We know that this is pressure is equal to unit weight times the height, the depth below. That's our normal expression as we write it. And so if you wanted, for instance, to be able to figure out how pressure changes with elevation as a function not only of unit weight, so this is the same as writing minus unit weight minus density of the fluid times acceleration in the z direction. And so since this is additive, if you like, I guess you could write this most easily as this. Right? So this is this term here that contributes to this. So if you're going upwards, accelerating upwards, you can imagine you add some increment to this. And so the fluid pressure that would happen as a result of that would be that this would be if you accelerate upwards at some acceleration in the z direction. And this is if the acceleration in the z direction is negative. So this would be negative. So, and you know that. It's the kind of things you feel in an elevator. And so we dealt with linear accelerations. So in other words, moving horizontally and vertically and or vertically at the same time. So we can say something about the inclination of a free surface and also how pressure changes would occur as you go down in the fluid. And we also talked about, this is basically that behavior here. And we also talked about rigid body rotation. So fluids that are turned at constant velocity, but because they are changing direction. So if you look at the fluid in plan view on the outside of this container as it goes around, the fluid wants to go straight in this direction at v theta, but because it's constrained by the tether or inside the container, it goes around at some other angle which is at angle to this. So it's going at the same velocity, the same speed, I guess, the same speed, but it's changing direction, and so therefore its velocity is changing. If its velocity is changing, it's accelerating because it's changing direction. So it's accelerating merely by virtue of the fact that it's changing direction. So this is turning at constant rotational speed. Omega is in radians per second. Revolutions per second are equal to 2 pi radians per second. And And so there's a conversion there. And so what you can do is exactly the same as we did for horizontal accelerating fluids. You can either say something about the inclination of this surface if it's an open container, or you can say something about the fluid pressure that you'd have at this end point, just by doing exactly the same things as we did before. So if you want to get the expression for the elevation of a surface in the container, it's given by this expression here. The elevation increases as you go radially outwards. As you double the rotational velocity, you quadruple the potential elevation, etc. This has a constant in it, and so in the example we did in class, we have to calculate the behavior for a meniscus where we know the value of this elevation, if you like. Again, positively upwards. Positive z is upwards. You need to get the value of a portion of this free surface at some location, at some radius. And so if you know the radius where the elevation is, and at some particular rotational velocity, and on some planet, you can calculate what the constant is. If you know what the constant is, then you can put it back into this expression, and then you can solve for any system that involves that. And so that's worthwhile knowing. And we did an example in class that does exactly that. Likewise, you can do the same thing to get the fluid pressures at some point. Define the behavior in terms of some location where you know the fluid pressure. So choose a place where you know the fluid pressure at a particular elevation, at a particular radius, and at a particular rotational speed. And if you know that, you have a value for the constant. If you know what the value of the constant is, you can substitute it back into this expression, and then you can solve for any system. We did an example in class like that. And so that's it. I don't know what else to do. I'm happy to stay. If people have some individual exams that you want to pull out and we'll go through, I'm happy to do that.